Hello, I am Alireza Khodamoradi. I will present our work S2N2, a FPGA accelerator for streaming spiky neural networks. This work is a collaboration between Xilinx Research Labs and UC San Diego. Why do we look for the next generation of neural networks? As we all know, current artificial neural networks are computationally expensive. In comparison, biological neural networks have less computational cost and are more capable. For example, a fruit fly is capable of processing audio and visual data. It can detect odor, navigate in a 3D environment, and much more. For example, it can dodge your hand if you try to catch it. A fruit fly does all of that with only 100,000 neurons and requires a ridiculously small amount of energy. Obviously, we have a long way to go before having artificial neural networks as capable and cheap as fruit flies. We will need new architectures and new training methods. Efficiency of the biological neural networks has inspired a new generation of artificial neural networks called spiking neural networks. S2N2 is a new accelerator designed for particular spiking neural network designs. In this presentation, we first review spiking neural networks and explain how they get their inspiration from their biological networks. We then explain input buffering and propagation delays in these networks. And after that, I will explain the architecture of S2N2. We then introduce new applications suitable for S2N2 architecture and review our results. We then review previous work and finish by providing a summary. In spiking neural networks, information is passed in the form of spikes. These classifiers learn pattern in spatiotemporal domain. Input and output of each layer are sets of spike trains. At each tick, each input can have up to one spike. For example, at t equal to 3, the upper and the middle trains have spikes, and at the bottom one, there is no spike. The input to a spiking neural network can be from an event-based sensor, such as event-based vision sensors, or it can be artificially made from non-spiking inputs. For example, an image can be transformed into sets of spike trains. In this case, each pixel is transformed into a train of spikes based on its intensity. The number of spikes or the delay between the spikes can represent the pixel value. For example, here lighter pixels have less number of spikes and darker ones have more spikes. The number of spike trains is equal to the number of pixels. The other difference between spiking neural networks and other artificial neural networks is the neural models used in these networks instead of activation functions. These models are biologically inspired and can include propagation delays similar to a biological neural network. In the following, I will explain the leaky integrate and fire model used in S2N2. This model is one of the most popular neural models used in applications, and it is mainly because the leaf model is easier to train and can be used to create more complex models. The leaf model has an internal memory for the membrane potential, shown here with the letter M. Its input is calculated by accumulating the weights associated with the receiving spikes. D is a decay value to forget the previous inputs, and T is a threshold that controls the output of the neuron. This model also has a reset mechanism that resets the membrane potential. I will quickly demonstrate how this model works through an animation. At T0, membrane voltage is 0. At T1, after receiving a spike from input 1, the membrane voltage is increased by W1. At T2, there is no receiving spikes, therefore the membrane voltage decreases, and this continues until T5, when the membrane voltage is increased by W2 because of the spikes received from input 2. It again decreases in absence of any receiving a spike until T8, when we receive another spike from 1. At this point, the membrane voltage is above the threshold and neuron produce an output spike. Then the membrane potential is reset. This reset mechanism creates a discontinuity in membrane potential. Other neuron models used in spiking neural networks behave very similarly with regard to their reset mechanism. And therefore, current training methods used for other artificial neural networks are not transferable to spiking neural networks. As mentioned earlier, new training methods are required to be developed to train these novel networks to fully uncover their potentials. Next, I will cover the input buffering and propagation delays, which are important to understand the S2N2 architecture. We can use a binary tensor of size st to store all the events in S trains with temporal length of t. If we use encoding, the minimum number of bits required to store these events is p st log st, where p is a spike ratio or 1 minus a sparsity ratio. This method is preferred for high sparsity ratios. Let me show you some examples. Here, with st equal to 8 and p equal to 25%, encoding events requires less memory. However, by increasing the size of the input to 1024, with the same spike ratio, binary tensor requires less memory. There are also custom encoding schemes that require more bits to represent an event. For example, address event representation uses 64 bits per event. In S2N2, we use binary tensors to store inputs to each layer. There are two ways to process these events. One, processing events at each tick, which requires less buffering and is more suitable for streaming. Two, processing all the events together, or tick batching, which requires larger buffers. In S2N2, we do not use tick batching. Due to the complexity of training, propagation delays in neuron models are not used in all spiking neural network applications. They also increase the implementation complexity. However, in a particular case, in feed-forward networks, fixed per-layer delays can be supported at no cost. Let me show you a simplified example. In this example, at t equal to 0, first layer received a green spike, and with no axonal delay, first layer can produce its output at the same tick. And because it has a synaptic delay, the second layer receives the input after 3 ticks. This delay propagates through the rest of the network. And when propagation delays are fixed per layer, we can simply pretend that there are no delays, process the events, and add the total delay at the end. Okay, we now can talk about S2N2 architecture. S2N2 supports leaf neuron model and feed-forward networks. It is built upon FIN architecture, and FIN is an experimental framework from Xilinx research labs to explore deep neural network inference on FPGAs. It targets quantized networks and is available at this link. At each layer, a sliding window unit applies interleaving on the inputs and prepares it for the next unit, which is a matrix vector threshold unit. MVTU applies the filters on the input and generates the output. MVTU is the core processing unit in FIN. It is used to build both convolutional and fully connected layers. FIN's pooling unit supports binary max pooling, which is suitable for binary spikes. In FIN, input can be processed in tiles by using the folding technique. The input buffer size in MVTU is equal to the kernel size, which is kernel width multiplied by the kernel height multiplied by the number of incoming channels. This is important to note because I will use this later in our results section. This is MVTU in FIN. Inputs and weights are loaded into the SIMD lanes, and MAC operations calculate the neuron's input. Then activation is applied to generate the output. To support the leaf model, We added memory for storing membrane potential. After loading membrane potential, the decay is applied to the previous value. In our applications, we trained our networks with a value for D that can change these multiplications to a number of shifts. To calculate the inputs, we only load weights if there is an associated spike. Therefore, our simulations perform accumulation instead of MAC operations. A selector is used to implement the reset mechanism for the leaf model. If neuron spikes at the output, 0 will be stored into the memory. The existing run counter in Fin is used for membrane initialization, and our code is available at this link. The unique architecture of S2N2 is suitable for applications with larger temporal dimension. We next introduce applications and our results. In automatic modulation classification, RF samples are input to the neural network for detecting their modulation. In non-spiking neural networks, in-phase and quadrature sample pairs, shown here in green and blue, has to be buffered for certain length before being fed to the network. We also can look at these sample pairs as events in the IQ plane. At each sample time, one event is observed in the IQ plane. We then can feed these events to a spiking neural network. 32-bit values for I and Q create a large input to the network. In our experiment, we quantized I and Q to 4 bits. Therefore, our network input is 16 by 16 binary tensor. To the best of our knowledge, automatic modulation classification using spiking neural networks has never been done before. For the first application, we used a 4-layer feed-forward network and radio ML dataset, version 2016, which has 11 different modulations. And each training example has 128 sample pairs, or ticks. Our 4-layer spiking neural network has similar layers to the non-spiking network used in the referenced work. Our network achieved a higher accuracy compared to the non-spiking network, and at clock period equal to 5 nanoseconds, this network can classify 173.6 thousand constellations per second. Here, we compare the input buffer size for each layer with tick batching. Each column is calculated by the corresponding equation below it. And on the right-hand side, you can see the spike ratios during inference. Without tick batching, input buffer size can significantly be reduced. Second network is a 6-layer feed-forward network used to classify radio ML 2018. This is a larger data set and requires a larger network. However, current training methods for spiking neural networks do not perform well on deeper networks. Therefore, we use a smaller network compared to other networks, other non-spiking networks used for classifying this dataset. Consequently, we achieved a lower accuracy. However, we observed that even by using only half of the inputs, or 512 IQ pairs, in this case, our network's performance did not change. The input to our network is also significantly smaller compared to other non-spiking networks. The 98% BRAM utilization in this here is the estimation result of high-level synthesis and is due to the membrane potential used for the leaf model. At clock period of 5 nanoseconds, this network can classify 65.1 constellations per second. Again, compared to tick batching, using binary tensors, storing storing inputs in S2N2 can significantly reduce the buffer size. Here, the reduction is more significant compared to previous work since the inputs in Radio ML 2018 have longer temporal length. Next application is an image classification example. The network is a feed-forward network and has 4 layers. Previous works applied the convolutional kernels on the membrane voltage. This requires MAC operations. In S2N2, we modified the network and applied the convolution kernels on the binary input, and therefore we only need accumulation operations to calculate the inputs. After retraining our network with the new changes, we achieved higher accuracy compared to previous spiky neural networks while having a network free of MAC operations. This network at a clock period of equal to 5 nanoseconds can classify 66.6 thousand images per second. And you can see the utilization on lookup tables, flip-flops, and DSP units is significantly low, while BRAMs are used for storing membrane potentials. The spike ratio in image classification example is higher compared to RF applications. This is because of the fact that in RF applications, we only had one IQ sample pair at input at each tick, while for images, many pixels can produce spikes at once at each tick. This higher spike ratio requires larger buffer size for input for tick batching and using encoded events. In comparison, using S2N2 with binary tensors and no tick batching, buffer size required for input are much smaller. In the next couple of slides, we review the previous work on custom implementation of spiky neural networks. As I mentioned, supporting general network topologies and propagation delays increases the design complexity. This is usually done with custom chip designs. These designs are usually expensive and less available to researchers. Some FPGA architectures support general mesh with limited support for propagation delays. For example, Blue Hive can support 16 different synaptic delay values and requires 16 FIFOs for that. The granularity of the delays are 1 millisecond. Or miniature that has to perform sorting on its input in order to support fixed axonal delays in a network. Most of the FPGA implementations support feed-forward networks and exploit the parallelism by tick batching to update the spike destinations in parallel. They also do not support propagation delays. As we explained, fixed per layer delays can be easily supported in feed-forward networks, and by avoiding tick batching, S2N2 can exploit parallelism similar to non-spiky neural networks, which requires smaller input buffers compared to previous spiky neural network implementations. All right, summary. In this presentation, we introduce S2N2, a streaming architecture for spiky neural networks. We showed that if sparsity is not high enough, using a binary tensor and avoiding tick batching can significantly reduce the buffer size. We also introduced 2 novel networks for RF applications on spiky neural networks. We then introduced an image classification example and showed that previous works can be adapted to S2N2 architecture by applying the convolution filters on the binary input. Thank you for listening. Our code is available at this link.